All right. Today is something a little different, I guess, than usual, but well, I guess not that different. Continuation of the sort of continuation of the intro to quantum computing series, but this is just really something that I've been sort of thinking about and working on for a little bit now, and that's Grover's algorithm. And so this is not a particularly super advanced quantum algorithm. It's just one of the more famous ones. But the reason I wanted to discuss this, since it's such a heavily discussed topic, it's been cited, what, I don't know, 10,000 times or something, is because I don't always feel as though there's a lot of good explanations or sort of understandings of it. So there's two things you'll see a lot if you try to research this, and you'll see sort of the mathematical proof using all of this direct notation, just going through the steps and showing, hey, look, this all works out right. But personally, for me, I don't find that to be very offer a lot of intuition. And then there's the more intuitive geometric approach, which I'll sort of go over, which is really common, especially in a more introductory examples. But the problem is, I don't really feel like that offers enough insight into the mathematics. So basically, Grover's algorithm is a method for unstructured search. So, if we have a list um, of n elements and we want to find, or maybe it's better if we simply write a function. If we have a function of x and it equals either, for a given value, equals 1, and there exists an x such that this is true. I guess I should write this the opposite, right? So, but what this is basically saying is, you can think of it as a list or you can think of it as a function, but basically, there's some query that you have that you can find the answer to, but you don't know what it is. So if you think of a list, right? If you're saying, okay, what element of this list is, the number 57, right? So then you would say f of 50, f of x equals, you want to know which value of x is 57. So this would equal 1 if it's, if, if, if this element, right, if x corresponds to 57, otherwise 0, right? This is sort of what the function would look like if we're mapping it. And so this is why you could think of it as unstructured search, right? Because you can do any of this and there's no order to this problem. And so this is what's known as an oracle-based algorithm, right? Because this function that we're sort of querying is just given to us. It's just known, or the algorithm just assumes it's there. And so I won't go into too much about the basics of this algorithm. There's a ton of resources out there just to get this super, if you don't know anything about quantum computing, then that's sort of the basic info is all there. But what I want to do is sort of go through an example of this and show how to sort of do this intuitively and geometrically. And so we can see that the basic idea of the oracle is we map a superposition of states. So we have an equal superposition of however many states that we have, however many qubits, right? We have 2 to the n states for n qubits, and it maps this superposition where it maps each state to a query. So for example, if you're looking at a list, the state 0 would be the first element, the state 1 would be the second element, and so on, right? And so then the correct answer would be you want to find the element, which would be the state that corresponds to what you're searching for. So for example, in this case, we would want to find the one that corresponds in this list to 57. Now, how you design this oracle is a whole challenge. What this oracle can do is a whole other thing. But all this oracle does, when we think from a quantum computing point of view, is it's a unitary operation, obviously. It's quantum computing we're talking about, that maps the superposition state, which is denoted S here. So that's an equals to superposition of however many n qubits you have, and it maps it to where it's the equal superposition of states, right? Where the states becomes the superposition. However, the correct answer, which is denoted as W or omega, I guess, and depending on how you write it, is denoted with the negative sign. So if you have this equal superposition here of, let's just assume for simplicity, 2 qubits, right? So you have 0, 0, 0, 1, 1, 0, and 1, 1. And then you do this oracle-based operation on it. And let's suppose, and I'll just assume this from here on out, that 1, 0 is the ideal state, right? This is whatever oracle function we're searching for, whatever unstructured search or whatever thing that we're trying to do, is that this is the answer. So what this does is this flips the sign. So everything else is the same. So this is the exact same, and it's just this is changed. And so that's all the mapping does. And now you might be wondering, well, why are we even doing this? Why do we even care about doing this algorithm? Obviously, since the quantum computers are, Turing machines, they can do any computation a classical computer can, but just because it can doesn't mean we have any interest in that. And that's because, and I won't talk about this and I won't prove this at all, but it can do this unstructured search in order of square root of n time, which is much faster than order of n time. It's a polynomial speed up over classical, right? Because think about it, if you're checking a list, you have to go through every single element in the list. Whereas this can do it in square root n time. And that's also been proved. That was actually, I think, proved before order time. But I won't discuss this or how this result is found, because, I mean, does it really matter? We know that it's that time, and that's really, from a pragmatic point of view, all that's interesting to me, at least. And so we can quickly see that this function, right, this oracle function is, hold on. Oh, no, sorry, I thought I wasn't recording. This oracle function is equivalent to, and I'll also be sure to you can find all the citations and all the resources where I was able to piece all this together from, all linked, obviously. I'll be sure to do that. But this oracle function, which I'll just denote UO, is this this representation, right? So this is the outer product, not the inner product. So this is going to be a 2 to the n by 2 to the n matrix for qubits, right? Whereas inner product would be a single value. And so we can see this, right? Because if you have some state that is, so this for the given state, for the target state, right? We can see that this yields, just distributing this, we can see that this is the result. If I just do this, and so we can see that this becomes, remember that this, because it's normalized, this just equals 1, and so we have w minus 2w equals negative. I know this is omega. I shouldn't be saying w. That's probably going to annoy some people. And so we can see it flips the state, and if you plug it in with just a normal state, right, with just like a non-target state, I should say, you can see that this term becomes 0 because they're orthogonal, because every state in a quantum, in a noiseless quantum computer is orthogonal. This becomes 0, so it cancels out, so we just get the identity times the state, which just renders it normal. And so that's just a little mathematical understanding. We'll see this sort of shape or does style right here become important later? And so what happens now? This is where you apply. So we have our superposition, and we have one state that is marked, or more. It could be more. There is Grover's algorithm does work for arbitrarily many target values, but I'm just going to assume one for now. And so assuming the equal superposition probability wise, just with the phase of this target flipped, right? And if you measured it, right, it would come out to the same probability. You would have that the negative sign changes nothing about the probability. You would measure it and you would get, equiprobable for every single result. So now what the Grover diffusion operator does is so we have our initial state, right, which we can see if this is the probability, this is the probability density, not the probability. So this can be negative, right? So this is each state, right? This is state 1, this is state 2, right? So we have our probabilities here, and then we go through to Oracle, and this is now our probabilities, right? And our target state is down here, right? And so the geometric interpretation of what's going on here is that the diffusion operator flips each state around the average. So right now, right, the average probability is like right here or something. So if we flip it around, then we get something that looks like that, right? You can see this is going up there, and these are going down. And so this is sort of the idea, right? And we can see we're increasing the probability of measuring that bit string. And so you can see that, this is sort of the geometric interpretation. You can also do it as angles because of the orthogonality conditions of these states. You can do this with an angular description, and the Qiskit page, which I also stole this this sort of diagram from, which I also have cited below, has an example too of this angular interpretation. But when you see the diffusion operator presented in literature, you're almost always going to see it in this following form: equals. Well, I want to make sure I do not tell you the wrong form. Yes, there we go. This is the form. This is Grover's diffusion operator. And so you can see it's an equal superposition, right? These are superposition states. And so we can decompose this operator into applying Hadamard gates on all the qubits, doing this operation, and then applying Hadamard gates again. And so this operation, representing it in gate form, is often the challenge or the implementation difficulties. But that's something we're also not going to discuss, right? Because the implementation I'm not concerned with right now. There is an existing implementation in the same GitHub repository that I have everything in, of this sort of gate-based version. So let's just look, what does this matrix look like, right? This is parameter independent, right? This matrix multiplication we're doing is parameter independent. So I can tell you exactly what this looks like. This looks like, so the 0, 0 outer product is simply 1 followed by however many zeros, right? So it's a completely 2 to the n by 2 to the n matrix with a single value being 1, and that's in the top left. So then we multiply it by 2, so we get 2 here, and then we subtract the identity matrix, which is just 1 in the diagonal. So we get 1, negative 1, negative 1, negative 1, all the way down, 0, 0, fill this whole thing out where only the diagonals, it's a diagonal matrix, only the diagonals are filled all the way down. And so this is what the matrix we're looking at is. So now let's consider an example, right? And this is really what I want to talk about. This helped me a lot when understanding this algorithm, and that is actually going through it, right? So you have this like everyone shows you the geometric interpretation, and you can get that pretty easily, right? It's not a particularly complex explanation. But then you're like, okay, what's actually going on here? I don't, how does this diffusion operate? You could look at this and be like, how does this at all do what I think it's doing, which is flip around the average, right? So it helps to step through it and see what's going on. So the first thing we have, right, is we have each state. We're going to start, right? We're going to do a 2-qubit example. So we have our oracled state where we have this. This is the input, right? So now let's do the Hadamard operation on it. So we do the operation on each qubit. And so this can change each state, right? So if we're doing Hadamard on each of these, I'm going to just represent each of these as the following, right? So keep in mind that h of 0 goes to, I'm just going to drop all probability notation and just work in numbers for now, just because I don't want to deal with all those fractions, right? And it works out, right? You can see the bigger number is more probable, even if it isn't normalized. So this goes to 0 plus 1, right? I drop the probability here, and Hadamard on state 1 goes to 0 and minus 1. So we can map this here to be 0, 0, plus 1, 0, minus, plus, sorry, 1, 1, 0, plus 1, 1, right? So this is what happens, right? If you applied a Hadamard gate to each qubit on the 0, 0 state, right? And that's what we did originally. And so then we do the second one, we can see the way I'm generating, right, is I'm just saying what would happen if you applied a Hadamard gate on this on each of these qubits in this state, right? We can see that the 1 qubit, anything with a 1, right, in this first part, oh wow, this should be 0, 1, right? This is 1, 0. Anything with a 1 in this second spot, right, it is getting flipped to a negative sign. So we can see that this second one maps to negative 0, 1, plus 1, 0. Because, I mean, I'm also not doing this fully out, but you could see, okay, if I did this out, right, this would be, you can separate each of these, right? So this would be 0, or maybe this one's easier, 0, and then 1, right? And so the Hadamard on 0, 0 would be 0 plus 1, and the Hadamard on that one would be 0 minus 1. So we combine them, we get 0, 0, we get 1, 0, but then anything with the second 1, right, is going to be negative. And so this is sort of what I'm just doing. You know, if you don't understand the gate-based operations, you might want to go back and review some more. So we do that one. Now we have, now keep in mind this has a negative in front of it already. So we can just do this one, 1, 0, and 1, 0. And now this one is going to have a negative in front of each of the values because it's a double 1 state. Okay, now let's add them up to get this final state, right? So this is going to be, if we think of the operation, right, of the algorithm as being the 0 state into the H gates into Oracle. Okay, maybe I should give myself a little more room. So it's going to be 0 states into superposition into Oracle into H gates into this 2, 0, 0 minus I operator into H gates, right? That's the general plan. So we're looking at it right here. So we're doing this H gate operation, and then we're going to do this, and then we're going to do this, and we'll see how that all turns out. So if we add these up to get the state right before doing the outer product diffusion operator, we see, okay, this is 2 minus 1 is 1 plus 1, so we get 2, 0, 0. These two cancel out. This one becomes negative minus, so this is going to be minus 2, 0, 1, and then these two is 2, 3 minus 1 is going to be 2, 1, 0, and this one, these two cancel out, and these two cancel out. So this is our state, right? Unnormalized state. So now let's feed it into this operator here, which we're going to do, right? So we have 2, 0, 0, minus 2, 0, 1, plus 2, 1, 0. And keep in mind, this is our solution state. We don't know it yet, but this is our solution state. So now we have our matrix, right, which we know is 1, negative 1, negative 1, negative 1, 0, 0, 0, 0, 0, 0, 0, filling the whole thing out, right? And we're applying it onto our state, which is 2, negative 2, 2, 0, unnormalized. So this might not work out. I guess I could renormalize this. If I just did that, it'd be 2 plus 2 plus 2 is 6. 6 squared is 36, which means that each of these would be square root of 3, because it's 3 equiprobable states, 1 over the square root of 3, I'm sorry. So I guess I could normalize that. Might as well just do it so the multiplication looks better. So this obviously is a new state of the same format, and we can see, okay, row times column, 1 square root of 3, row times column, 1 over square root of 3, row times column, it's negative 1 square root of 3, 0, right? So this is now our new state. So now if we apply a Hadamard to it, and you can sort of see now what this inner diffusion op is doing, right? It changed the place of the negative, right? Nothing, the probabilities don't get modified at all here. Only the phases of these probabilities do. And so that's sort of the intuitive thing that you get from doing all of this out is, okay, the probabilities aren't changing until the second Hadamard case. The phases, that didn't change, because remember, if you have this Hadamard gate, it relies on these phase operations to convert between zeros and ones, right? Because if you have 0 minus 1, that converts to a 1. And so these are important when applying the Hadamard gates, but this inner op, this is the 2, 0, 0 minus I op that we're doing right now. So now we have the final Hadamard process, which we can do here. So we have 1 over square root of 3, 0, 0, right? Because it's the same as before, 0, 1, 1, 0, plus 1, 1. And then we have 1 over square root of 3. And this is 0, 0, negative 0, 1, plus 1, 0, minus 1, 1. Because this is the state we're working with. So the second ones are negative. And this one is positive because it's a 1 in the first place. It's a negative 1 square root of 3, 1, 0, 0, minus, plus, sorry, 0, 1, minus 1, 0, minus 1, 1. So let's add these up, right? Okay, this one is 2/3 minus 1/3. We get 1 over square root of 3. Oh, I don't know. I want that parentheses, 0, 0. Okay. Now let's add up this one. We get, this cancels. We get a negative 1 over square root of 3, 0, 1. We get a 3 over square root of 3, 1, 0. And we get a negative that cancels out, a 1 over square, oh, I should add a plus here, root of 3, 1, 1, right? And so now you can see, obviously this is once again unnormalized probability distribution, but it doesn't really matter. These numbers are just placeholders in effect for the relative densities. We can see that this state is now the most likely state. And so we can gain some intuition into, by doing all of this out, we can see what's really going on in that diffusion operator. And we can see, well, it maps it to a phase adjusted, right, basis state. When you're using these Hadamards, right, it collapses, well, I shouldn't say collapse because you're not making a measurement, but it reduces the number of states. And then when you do this operation that manipulates this inner diffusion operation that manipulates the relative sign of the probabilities and then re-Hadamard them or re-expand them, you can see that the effect here, right, is this flipping over of the average. And you can sort of see in this matrix how this would sort of come to play. And so it's not a super intuitive explanation, but I found it to be extremely helpful just to go through this. And so now, obviously, we have to go through this in code. And we're going to use some made up gates. And so we can see, let me do this, there we go. So this is the idea, right? Where this is just in circ. This is the number of qubits. This is how many repetitions. If we do oracle, diffusion, we can increase our certainty, right? Because you're flipping around that probability more and more, that average probability more and more. We create the circuit, we run it, we get the results. I just made a super simple oracle that's for the all one state. So for 1, 1, 1, 1, 1, 1, 1, however many ones we have, that's it, which you can do easily by just using a controlled Z operator. And so then we have our circuit, right? So we make the qubits, however many we need, and then we apply an H gate on all qubits to create our initial equal superposition. And then we apply the oracle, we do the H gates, we do this inner diffusion operator, we do the H gates again, and then we repeat it. So this is just the oracle, right? Just the controlled Z operation. The H gates are explanatory. But this is what I want to talk about, this custom Grover diffusion operator gate. We can see that when it's initialized, we get the unitary, which is this, right? 2 times this 0 state, right? I initialize it all to zeros, and in the initial position, I put a 1, and then minus an identity matrix. I can actually print this too. And then we just do this unitary operations on however many qubits we need to do, which is initialized here, and we get the result. So if I do this, let's see, let's zoom in a little maybe. Let's do Python. We can see that it'll take a second because it has to initialize everything. So you can see this is the unitary operator for 3 qubits, which is 1 and then all negative ones. So we have this initial superposition. This is the oracle. This is the first Hadamard, the inner diffusion operator, second Hadamard, and the results. And we can see that by a pretty substantial margin, we measured the correct results, which is 1, 1, 1. And we can see that if I do this for, let's do this for maybe 10 qubits, and let's repeat it 3 times, right? We should expect to see a substantial increase, or maybe not substantial, but a definite, oh God, yeah, you can see there's a lot of, oh yeah, but you can see, okay, maybe 10 qubits was a lot. Let's just do 5 qubits. That might make it easier to see all of the outputs. So you can see here that we are, yeah, the graph is, or the unitary is hard to see, but you can see we're repeating this set from here to here over and over again. And we can see by a substantially larger percent-wise margin that the result is correct, right? This is 900 or like 90% as opposed to like 70% that we had last time. So yeah, that's basically it. I just wanted to offer some intuition into this Grover's algorithm, just some simple code to go along with it. And yeah, that continues the sort of intro series.